Hello all of you. Welcome to my second ever video. In this video I shall be talking about decision trees. Uh, so in some sense this video is going to be similar to the first ever video that I had created, which was quite a while back. In that video I had talked about information theory, but more importantly I had basically laid out the intuition behind the information theory so that those concepts could be easily understood and then applied in practice later. So very similar to that, I would lay out the intuition behind decision trees in this particular video. I would try to explain the concept in a very natural way so that the complexity doesn't overwhelm anyone. And then basically people can apply decision trees in their applications later on. One important prerequisite before you go through this video is that you should go through my first video, because in the first video I laid out some concepts of information theory which I shall be using in the second half of this particular video lecture. So with that said, let's get straight into it. So with decision trees, we primarily attack problems wherein we are dealing with classification. So let's see what I mean by that. So the classification problem is that given some input variables, which could be continuous, which could be discrete, it doesn't matter. I want to predict the class of a discrete output variable. So my output variable is discrete, it is not continuous, and given a bunch of input variables, I want to predict the class of the output variable. So let's get a little more specific with an example. And that example could be, say, credit worthiness of a person. So whether this person is worthy of receiving credit card from a bank. So the input variables could be things like age, work experience, salary, whether the person is a graduate, whether the person has a past conviction, whether they have run-ins with the law, does the person own a house, etc., etc. These are very simple factual questions, the answers to which could be easily ascertained, right? So basically all you need to do is do some background check to get to understand each of these variables. And in terms of the output variable, we have a single output variable, and it's a discrete variable, and in this case it's a binary discrete variable, and we're basically asking whether this person is worthy of receiving a credit card or not. So that's the classification problem, and decision trees are used to solve classification problems such as these. So let's quickly look at the outline of the steps involved in solving classification problems. So the first step is you typically would collect a lot of data, a lot of samples where you know the input variables as well as you know the output class. So you would have, let's say, 10,000 or 100,000 or potentially 1 million customers or potential customers. You would have their factual data around their age, their work experience, all the attributes that we discussed, and you would have an annotation against each of them that says whether this person would have been worthy of receiving credit or not. Okay, so that data has to be collected, because if you don't have data, you can't do any learning. Okay, the next step is to randomly select 80% of the above samples, and we will call them training data, and the remaining 20% we'll call as test data. Now this 80-20 split, you could go with 70-30, you could go with 60-40. You can choose to have it done your way, but the point is that you will sample some records and call them as training data, and some of the rest of them would be called the test data. Now you use the training data and you build an ML model using any of these supervised learning approaches. So one could be decision tree, which is what we are going to understand in much more details in this video, and another one could be, say, logistic regression, and then there are others as well, like neural networks, etc. as well. So in this particular lecture we will only be focusing on decision tree, and we'll be talking about the intuition behind decision tree. Okay, and finally you would evaluate the model performance on the test data. And when we evaluate the model performance, basically the metrics that we're looking at are precision and recall. So I'm not going to talk about what precision and recall are. I'm assuming that people who are watching this video are already aware of those concepts. If you aren't, then you can go to the Wikipedia link that I would refer to in the description. And it's a very good link. It should explain the concept very easily. So you can come back to this. You can take a pause and you can look at that Wikipedia page and then come back to this video once after you have done so. All right. So now let's get into it. Let's understand decision trees. Let's start to build the intuition behind decision trees. Okay. So we'll talk about a naive way of classification before we actually start talking about decision trees themselves. Okay, so let's say that you have a problem in which the output variable is discrete binary, which means it can take only discrete values and it can take only two possible discrete values. And let's say those values are A and B. Simple as that. Okay. Now in the training data set, let's say A occurs 70% of the times and B occurs 30% of the times. Okay, so let's say in a random sample, we will find that 70% of the population that applies for credit card is deemed as credit worthy. So 70% of the times you're getting A in your training data, and 30% of the times you're getting B. Okay, this is just how your training data is distributed across the all possible class labels. Okay. So a naive classifier could say, I will always predict A irrespective of the input variables. I do not care what the input is. I do not care what the input says. I will always say A because A has the highest occurrence in the training data. And just because we have taken test data and training data from the same distribution, we would expect it to have highest occurrence in the test data as well. So because A would have highest occurrence in test data as well as in training data, my classifier just says that I'm going to predict A. Simple as that. That's my naive classifier. Okay, so I just wanted to clarify one thing here. This is, there is no such naive classifier. This is being said here just to build up the intuition. Obviously, for there is no benefit of having such a classifier, so there is no such thing. So please don't confuse it with something like a naive Bayes classifier, which is a wholly different concept. Okay, so we'll move on to the next slide, but all we've done is we've said whichever label has the highest occurrence, that's what my classifier is going to predict always. Okay, now let's see what are the drawbacks of that. Pretty intuitive what the drawbacks are. It does not use the input variables at all, so therefore it is not learning anything. It's just foolishness, right? So why would you want to build such a classifier? The second drawback is you have zero control over precision, because precision in this case is just equal to the occurrence of max occurring label, right? So if the max occurring label, which is A in this case, is occurring 70% of the times, your precision would also be 70%, because in test data set also you're assuming that 70% of your test data samples are classified to A. Now we know that test data and training data performance don't match, but just bear with me for a while. What you do find, or what you are likely to find, is that precision is just equal to the occurrence of max occurring label. So whatever precision goal you are likely to define for your problem is not going to be met because you have zero control over it. You have absolutely no control over precision. You can't improve it. Okay. We understand this. But why did we discuss this? What was the point of discussing a naive way of classifying, right? So let's see. There was a important reason. There was an important reason that I brought this up. So let's talk about a peculiar case. And let's say the peculiar case is this. So say my supervisor has defined the precision goal for a particular problem as 90%, okay? And the label A occurs in training data more than 90% of the times, okay? Now, with whatever we just discussed above, the precision is basically the occurrence of max occurring label. What seems to be the case, or what is obviously the case, is that the naive classifier itself satisfies the precision goal. Okay. Now, it may look like cheating. It may look like we didn't do much. We didn't actually learn. We still did not use the input variables. But the point is, did we really need to use the input variables at all? If all I care is having 90% precision, and by very nature of this data set, I know that 90% of my records are going to be classified as A, I could just always classify all inputs to A, and then just wait for the system to work. So that's what it is, right? So I'm basically achieving my precision goal, although I didn't do much, right? So now, of course, we don't do that, but this hopefully has helped you build some intuition, some early intuition behind what we are going to do in decision trees. So let's see what we are going to do. Let's say I have a data set where the occurrence of max occurring label is 70%. Okay, so my naive classifier can only give me 70% precision. Okay, but the precision goal that I have is 90%. So the precision goal is obviously more aggressive than what naive classifier can give me. But here I can now use the intuition. I could try to split the data set S into multiple smaller data sets by partitioning using input dimensions. So what do I mean by that? Let's say I could partition based on work experience. So I could say I'm going to partition S into two data sets, S1 and S2. In the data set S1, I will have all the people who had less than 5 years of work experience. And in the data set S2, I'm going to put all the people with greater than or equal to 5 years work experience. I'm going to partition the data set along those lines. Now, when I look at partitioned data sets S1 and S2, now the occurrence of the max occurring label in each of those data sets would change. It would no longer be 70%. Okay, so because we do assume, we do hope that work experience does contribute towards credit worthiness of a person. So you would find typically that the population that had, say, more than 5 years work experience, probably they would have a much higher credit worthiness, right? So they are more likely to be credit worthy, right? So the distribution is changing now. So the occurrence of max occurring label would no longer be 70%, it would change, okay? So that's what the intuition is. If we are able to create these splits in such a way that each of the smaller data sets has occurrence of max occurring label as greater than equal to 90%. Okay, so each of these, so 90% one way or the other, it could be 90% true, it could be 90% false, right? All of these data sets together have a 70% true, but some of these will have 90% false, some of them will have 90% true, right? Most of them will be in that 90% true bucket, because overall I'm having 70% true, but there will be some cases where I will have 90% false as well. So if I'm able to create these partitions in such a way, okay, that each of my data sets, each of my smaller data sets, has an inherent bias. Okay, is more likely to be one label than the other. Is much more likely to be one label than the other. In fact, 90% probability. Then all I need to do is I need to use naive classifier on each of those small data sets. Okay, and when I say 90, the naive classifier, all I mean is predict that very label, right? So the bucket that has 90% trues, it should just say, I'll predict true here, and wherever it says 90% false, it should just predict false there. As simple as that. So all I need to do is somehow split S into multiple smaller data sets such that I can, have so that I can create a bias in each of those smaller data sets. Okay. So this is the core intuition behind decision trees. That's the heart of the intuition. But still, we are not done yet, right? As you would obviously see, is that we have pushed the problem elsewhere. Okay, we have now washed our hands away from classification problem, and we have now invented a different problem for ourselves, which is how do I best split these data sets? Okay, so take a pause if you want to. So far I haven't discussed much. I have just laid out the core intuition behind decision trees. Now I'm going to be a little more slower in the next few slides, so that because those concepts are a little more difficult. But here you can see that we have laid out the first basic intuition behind decision trees, and we have changed the problem now. The problem is no longer classification. I have a classifier now, but there is some other aspect of the problem that still needs to be solved, which is basically how do I create these smaller data sets. So we will do that by an example. Okay, we will handcraft a decision tree, and then we will lay out the intuition for it, and then we'll see which ideas work, which intuitions work, which intuitions do not work, and then we will create an algorithm. Okay, so let's handcraft a decision tree using some assumptions. So I'm still talking about the same problem statement, creditworthiness. Okay, the training data has 1 million samples. So as I was saying, the trues are 70%. So yes is 700K and no's are 300K. So 700K records, the person is deemed to be credit worthy, and 300K records, the person is deemed to be unworthy of receiving credit. Okay. Let's take one particular feature, and let's say that feature is, does this person have a prior conviction? Has this person had a run-in with the law? Okay. And again, this is a complete hypothetical. Say 100K people have had prior convictions. Now this is a very large number. We are basically saying 10% of the people have had prior convictions. In some countries that might even be true, but in most countries it wouldn't be. But this is just a hypothetical, so bear with me on it. So 100K people have had prior convictions, but here is the important thing: 95% of those people are rated as unworthy of receiving credit. So they are tagged as not worthy of receiving credit. Okay, so that basically simplifies the problem, at least partly. We'll see how. Okay. So we'll handcraft a decision tree using the above feature, and what we'll do is, if you look at this, the parent node, the root node in this particular case, because the tree is just starting, but because we are not going to ever look at the full tree, we'll look at only the parts of the trees. So I'm going to say parent and left and right child. And tree is recursive in nature, right? So the left child could be parent of its own subtree, right? So the same analogies apply thereupon. But the thing is, so in this parent, you will see that the question that I've asked is, does this person have prior conviction? Now, there are two branches that are going out of this parent node. Yes branch, which is going to the left node. No branch, which is going to the right node. There could be more than two branches as well, but again, I'm keeping things simple for now. So I'm assuming that this particular discrete variable also had only two possible options, but there could be more. Now, before asking this question, my data set was as follows: 700K people, yes, they are credit worthy. 300K people, no, they are not credit worthy, which means I have 70% yeses. Okay. Now let's follow the yes branch of this particular tree. So you would find that I have not written anything in the node because I'm not asking any other question yet. I'm just trying to show what happens when I ask this particular question. So now let's see how the distribution changes though, the credit worthy people. So in the yes side, I have only 100K people as we had discussed earlier, and 95% of them are unworthy of receiving credit, right? So basically yes is 5K, no is 95K, which means this distribution is overwhelmingly no, and that's 95% no. Okay, 95% of people in this population are not worthy of receiving credit. Now let's follow the no branch of this question. So does this person have prior conviction? Let's say he doesn't have a prior conviction, and that's the right child. And in the right child, I have the remaining 900K records. Okay, and the yeses would be 695K and the no's would be 205K. Okay, and if you see this, if you see the right child, that has 77% yeses. So 77% of the people are rated as being worthy of receiving credit. Now let's evaluate this particular tree. Let's think a little bit more on this. What has happened? What has happened is that in the parent node, I had 70% yeses, 30% no's. So my split wasn't that strong. In my left branch, in my left child, I have 95% no's and only 5% yeses, which means I have a very, very strong indicator. I have a very strong split. And in fact, I have already achieved my threshold, the precision threshold that I was aiming for. In this particular branch, at least, I have achieved it. In the right branch, in the right node, you would see that I have 77% yes and 23% no's, right? But this is still better than the parent. In the parent, I had 70% versus 30%. And in the right child, I have 77% versus 23%, which means I have a stronger indicator in the right child. So what this shows is that this particular question has helped us move forward. It has helped us, split the distribution in a much more focused way, so that the data sets are tending towards one particular class label, which means it is a good tree. But how do I quantify this? Because I mean, theoretically, I can see that this is good. How do I quantify this? How do I say that this is a good tree? Right? How do I conclude, or how do I, what sort of a metric can I use to evaluate the quality of this tree? So let's do that. So at the parent node, you would see that the 70% yes and 30% no's, which means there is, if you remember from my previous video, this particular distribution would have a high entropy because it has a high degree of uncertainty. There is a chance of yes, there is a good chance of yes, but there are good enough chances of no's as well, right? So there is a good amount of unpredictability, which means it has high entropy. Low amount of predictability, good amount of unpredictability, which means it has high entropy. On the yes branch, 95% no, very high degree of certainty. That means I have low entropy. Likewise, in my right branch as well, the entropy is lower than the parent because I have higher certainty or lower uncertainty. So I have lower entropy as well. Now, these are the entropy values. So the parent entropy is 0.88. You can quickly validate that. The left child entropy is 0.29 and the right child entropy is 0.78. And as you can see in this particular case, the parent entropy is greater than both of them. It's greater than the entropy of the left child and it's greater than the entropy of the right child. So we now know that we can use entropy as some sort of measurement for deciding the quality of the decision tree. So we are going to talk about information gain, and we are going to use these entropy values. But the problem is I still don't know how to combine the entropy of, which entropy is more important, whether the entropy of the left child was more important in this case or whether the entropy of the right child was more important. Because the left child had an entropy of 0.29 and the right child had the entropy of 0.78. They themselves have a very different entropy values. They are both lower than parent, right? But they are themselves very different. So which entropy should I use? How should I compute the information gain, which is going to be a metric that I would use to decide the quality of this decision tree. So let's see what we come to. So a mere repeat of what we just said. Decrease in entropy from parent to child is desirable. Low entropy means high predictability, which in turn means one label will dominate over the rest in that subset. We want to maximize this entropy decrease, and we are calling this as information gain. But the problem is, how do I measure it? Because while I know what the parent entropy is, for the child I'm confused which one to take. I don't know, right? So let's start with some basic intuition. Let me say that the I'll basically do a parent entropy minus the min of entropy of the left child and the right child, right? So the parent entropy in this case was 0.88 and the left was 0.29 and the right was 0.78. So I'll basically go with 0.88 minus 0.29. That would be my information gain. And that looks okay-ish, but I still need to delve a little deeper to see whether this is actually a good metric or not. So moving on, before we evaluate whether this was a good metric or not, let's take a different feature. Let's say that feature is, did this person study from some college named ABC College? Okay, so I don't care what this ABC is, what this ABC isn't. All I'm saying is, did this person study from this college? Okay, and let's say in my training data, I have only 2 records of people who studied from ABC College, and both of them were deemed as creditworthy. Okay, so there are only 2 records of people studying from ABC College, and both of them are deemed as creditworthy. So let's say, had I split on this particular question, the question being, did this person study from ABC College? Then let's see what my decision tree would have looked like. Well, this is what it would have looked like. So again, on the parent node, you would see the question says, did this person study at ABC College? Alongside that, I have the distribution of creditworthiness, which is my output variable. Yeses are 700K, no's are 300K, so 70% yes. Okay. Now the question that I asked, did this person study at ABC College? The yes branch, as we said, only 2 people are in the yes branch, and both of them are creditworthy. So you can see in the yes node, the creditworthiness says yes is 2 and no is 0, and it's 100% yes, which means the entropy of the left child is 0.0. Okay, because it's only one label, it's only a single label, so there is no entropy. And the right child, bulk of my records will go into the right child. So it has 699,998 yeses and 300K is no. And if I look at the percentages and the entropy values, it's quite similar to the parent. Okay, it's not substantially different. Okay, so the right child has a very similar entropy to the parent, but the left child has a very, very low entropy. It has an entropy of 0.0. So which tree is better? Well, based on the information gain metric that I have created, because I'm looking at the min of HL and HR, in this particular case, the min of HL and HR is 0.0, and the information gain therefore is 0.88. Whereas in the previous tree, the information gain was 0.88 minus 0.29. So it looks like here I'm getting more information based on the metric that I have created, which I don't know whether it's a good metric or not, but at least that metric seems to suggest that tree 2 is better. But now let's critically evaluate that. So let's compare the two decision trees that we have just seen so far. So as I said, the proposed formula for information gain prefers the second tree as the entropy of the left child vanishes to 0, and the formula only cares about the min of the entropy of both children. Okay? But the question is the second tree really better? Do we think that the second tree is going to work better in the test data set? So let's look at this particular case. Let's say there is a person in the test data set. You have a person that passed out from ABC college and also has a prior conviction. This is important. This person has has graduated from ABC college, but that person also has prior conviction. Let's see how tree 1 is going to respond to this person, and let's see how tree 2 is going to respond to this person. So in tree 1, the very first question that we're asking is, does this person have a prior conviction? The answer is yes, this person has a prior conviction. And if you remember what the first tree said, it said 95% of people who had prior convictions are rated as credit unworthy. Therefore, I'm not going to give credit to this person. I'm going to rate him as credit unworthy. So this particular person by tree 1 would be credit unworthy. Likewise, by tree 2, because tree 2 is only looking at ABC college, that's the very first question that it asked. So the tree 2 is going to say that this person is credit worthy because all the people that it has seen from ABC college were deemed as credit worthy. So tree 1 rates this person as credit unworthy with 95% confidence, whereas tree 2 has absolute confidence that this person is credit worthy. It has 100% confidence. But the problem is this. Tree 2 has considered only 2 data points. It had only 2 data points where in training data we had people who graduated from ABC college. In that particular branch, there was only 2 data points. Whereas in tree 1, in that particular branch, there were 100k data points. So tree 1 naturally is better because it has looked at far more data points and therefore is much more likely to have generalized better. Whereas in tree 2, that particular branch that we followed, it had so few samples that we have very low confidence in whether that branch will generalize well or not. So tree 1 is actually better, but the info gain metric that we had created was actually preferring tree 2, which means we have to discard it. We have to discard this metric. But before we discard this metric, let's see what went wrong. What did we do wrong? Why did it prefer tree 2 instead of tree 1? Okay. So what happened is, by considering the min of the entropy, so we only anchored on the min of the entropies. We never cared what the other entropies were. We didn't care what the max was. What we did was we forced the min of the entropy to be as low as possible. And what that means is, what that essentially did is, it splitted the data set very unevenly, such that very small data sets And you see, if your data set is small, it is quite likely that it is going to be biased one way or the other. And since it was a small data set and it was biased one way, the entropy was low, right? So basically what we did was we forced the tree to create two very highly uneven data sets. One particular data set had only 2 records, and the other one had 999,998 records, right? So it's very uneven split. And the smaller data set naturally had very low entropy because it had very less records. In fact, if it had been 1 record, then by definition, 1 record will only have 0 entropy. But so that's why I took the example of 2 records in this case. So what it did was it forced it this way. It forced the data set to get partitioned this way. And because of statistical flukes, because we had very less data on people who had graduated from ABC college, and it could just be a statistical fluke that both of them proved to be credit worthy. So we ended up prioritizing the statistical flukes and anchoring on those. So clearly min was flawed. Okay, min was flawed. What about max then? If I consider max in the information gain, what I'm going to do is I'm going to make sure that all of my child data sets have low entropies. Right? That's what I'll end up doing. All of my child data sets should have as low entropies as possible because the max itself has to be low. So let me replace min with max and let me now see what happens. Well, in principle, this should work better than min, but it still is going to be not very effective. So let's consider a different tree to see why max also has a problem. So consider monthly income as a feature, and let's say it leads to the following tree. Now let's look at the tree. So does this person earn more than 500K per month? Yes or no? Okay, so again, 70% in the original distribution are credit worthy. But if the person earns more than 500K per month, let's assume for a moment that all the people who earn more than 500K per month are credit worthy, and there are 400K such people. So then in the yes branch you have 400K people, and all of them are in the are rated as being credit worthy. None of them are not worthy of credits. So that's a 100% yes bucket. Okay. On the right child, you would see now you are left with 300K people who are credit worthy and 300K people who are not credit worthy. Okay, so it's a 50% yes. Now this is a more even split. Okay, so what you would find is at the parent side, the entropy was 0.88. It was high. On the left child, I've managed to reduce it to 0. And I think it's still a good split because my left child and right child are comparable in their sizes. The left child has 400K and the right child has 600K records. So it's still kind of an even split. So the left child, the entropy has vanished to 0. Great. But the right child, the entropy has actually increased. It has now increased to 1.0. Okay. Now the problem is, if I therefore go by max, because if I apply the formula for info gain wherein I'm considering max, this would suggest that I'm actually losing information. Instead of gaining some information, instead of gaining some positive information, I have lost information. But in reality, this question was still helpful. What I would need to still do is that the right child still needs to be further broken up, right? I need to still work on the right child. The left child is done, but the right child still needs some more work. Agreed. But does that mean the question was bad? No, it still was incrementally better than where I stood earlier, right? So it still helped me get to this situation, and now I can focus only on the right child and split it accordingly. So this was still a valid, valuable question. But if I look at max, then it is basically giving me a negative information gain, and it's sort of suggesting that this is actually counterproductive, which is not the case. This is not counterproductive. This is absolutely valuable. This question was good. Okay. So take a pause if you need to, because in the next slide we'll pretty much introduce what the real metric is. Hopefully you understand the intuition so far, the min and the max, and you should understand why these haven't worked. So let's look at the next slide. So max and min have ignored entropy of all but one child data sets. Max has looked at only the max child, the child data set that had the max entropy, and min has only looked at the child data set that had the min entropy. They have also ignored the relative size of each child data set, right? So clearly max and min are not suitable in this formula. I need to combine the entropy of left child and the right child in some other way. So what about simple average? Well, it turns out that the simple average is still missing out on the relative size of each child data set, right? I have taken into account, I have, factored in the point A, but the point B is still ignored, right? The relative size of each child data set is still not taken into account. So let's take an example. If 90% of training data points go to the left child, then in test data also, I'm likely to have 90% probability of going to the left child, right? So its entropy should matter more in this equation. In this formula, its entropy should have higher weight, and the entropy of right child should have lower weightage. Okay, so as simple as that. I need to basically change simple average to weighted averages, and so in this particular formula now, HP is again the entropy of the parent. Small n sub L is number of items in the left child, number of records in the left child. Small n sub R is the number of items in the right child. Capital N is the total number of items, which is basically NL plus NR. And HL and HR are the entropy of the left and right child respectively. So this is what my formula is. The metric that I would use to evaluate my decision tree is this. I will basically compute the entropy of the parent. I compute the entropy of the left and right child. I will factor in, what is the relative size of each child data set. Basically plug this formula and figure out how much valuable this tree is over other possible trees, over other possible alternatives. Okay, so this is this should tell you, which tree is more important than the other. Now that part is at rest. Now we can basically build a formula or build an algorithm that uses this formula to create a decision tree. And that's what we are going to do in the next slide. So the algorithm is therefore this. I start with an input distribution S. I check if my terminal criteria is already reached, and if it has already reached, then I stop. What does it mean? We'll come back to it. If the terminal criteria is not reached, what I'm going to do is I'm going to calculate information gain for all possible ways I could have constructed the tree, or at least the very first question that I could have asked. So for all possible questions, I'm going to see how they are subdividing the distribution S, and based on all such possibilities, I will calculate the information gain. and I'll choose the question that maximizes the information gain. Now you may ponder, what do I mean by all possible questions? Right? So what is the universe of all possible questions? So bear with me for a minute. That's what we're going to discuss in the next slide. So, but assuming you have the universe of all possible questions, assuming you know what are the kind of questions that can be asked about this distribution, assuming you know that, you can figure out the information gain for each possible question, and then all you need to do is choose the question that maximizes this information gain value. So in the step 3, we basically split the sequence, the distribution S into the child data sets based on the above question. And in step 4, we repeat steps 1 to 3 for each of the child data sets. Simple as that. That's my algorithm. Nothing fancy about it. Very simple. We said we are going to talk about terminal criteria, right? So when do I basically stop? When do I know when to stop? So for a very naive variant of decision tree, let's define a very naive variant of decision tree, and we'll see later why this naive variant is not a good option. But for a very naive variant, you could continue to split until all samples in the distribution belong to the same class. Okay, so I started with 70% yes and 30% no, but what I want is at the leaf nodes, I want either 100% yes or 100% no. I don't want anything else. I don't want 90% yes, 10% no. I don't want any of that. So I'll basically draw out the full tree. Okay, that's basically the naive variant. You can think of it that way, and we'll see why that's a terrible strategy in a later slide. But for now, just assume that that's how we are doing things. Okay, so let's talk about the universe of questions, because we kind of glossed over it. We said that if I know all possible questions that can be asked about this distribution, I have a way of prioritizing a particular question, the one that I'm going to ask right now. But how do I come up with this corpus of questions? How do I come up with the universe of questions? That's what we'll discuss now. So let's say we arrange, for each feature, we arrange the values of training data in some sort of a sorted fashion. Let's say we have the feature is monthly salary. And let's say the training data set has the following unique values: 100K, 200K, 300K, and 500K. So now what kind of questions can you ask? You can, or how can you split this data set? Basically, the way you can split this data set is anything below, less than or equal to 100K, anything between 100 and 200K, anything between 200 and 300K, anything between 300 and 500K, anything above 500K, right? So the last one is pretty obvious. Anything that is not anything that does not subscribe to any of the previous questions is obviously going to fall into the latter. So, but the point is, you can basically subdivide your distribution using those splits. So we can ask these kind of questions: is salary below or equal 100K, salary below or equal 200K, etc. Okay, and that's how we can divide this distribution. The question is, why not a question like is salary below or equal 150K? Now 150K doesn't appear in the training data, right? So what is going to happen is, from a training data standpoint, 150K and 100K are going to split the training set identically. And that would mean equal precision in training data. Both the trees will have equal precision in training data. However, their test performance would differ. But the problem is, I don't have a way to know how much their test performance will differ at the training time. At the training time, I'm not allowed to cheat. I'm not allowed to look at the test data set, right? So I have no way of knowing whether 150K is actually going to work better in the test data set then 100K or 125K or things of that say, things of that sort. So which is why we don't need to um, consider any other value. All we need to consider are the values that I actually see in the training data set. Okay, so for this particular dimension being monthly salary, I have 4 possible questions because I have 4 possible values that I see in training data, which means that a max number of questions that I can have is n times d. For each of my dimensions, I will have n possible questions, and n is the number of training data records. So for each of the dimensions, I will see, for each of the dimensions, I'll go through all my records in the training data. And let's say all of them have unique values in that dimension. Then I have n possible questions. So it's n times d. And the n times d is the max estimate because typically you will have some values that coincide as well. So wherever the values coincide, you will, it will no longer be n, it would be n minus some delta. But in any case, this is the absolute maximum. N times d is the max number of questions. And you have a way to now create those questions. So the algorithm of decision tree is now complete. As we have seen, if I have to just kind of summarize, we have seen how we can ask various questions that split the data into smaller data sets. That's number one. Number two, we have seen which questions should take precedence over the other, which way of changing the which way of choosing the subsets should be preferred over others. That we have seen by a metric called information gain. And the third is, well, I keep going on until I have reached some threshold criteria, and that's in the naive way I said that it's 100%. Earlier I was saying 90% precision, so I could do it till 90%, but in the most naive way I could even go up to 100%. Right? So we'll now touch upon this particular aspect a little more, the third aspect a little more. What determination criteria should be, right? Why going to 100% might be a bad idea. Okay. So basically it's called overfitting to the training data. So let's take this example. So let's say, and now I don't care what the application is. Let's say I have my dependent variable, the output variable is the distribution says 9999 yeses and 1 no. Okay, but I do have a question X that will split this into 2 distributions. One of them has only one data point, and that's the one where the output variable is no. And in the other one, I have 9999 data points, and all of them are yeses. So my decision tree looks like this, right? You may think that going down to 100% is better than staying at the parent, which has 99.99%. But the problem is that the left child might just be a fluke, right? So you are potentially losing generality here. You are adjusting to some natural flukes in any distribution. So any distribution is going to have some sort of statistical flukes, and you are overcorrecting for that. You are basically overfitting to that, and it's not going to generalize in the real world. In the test data set, it's not going to hold true anymore, most probably. And that's basically it. That's what overfitting is. You ought not to have split this data set furthermore. Like it was already 99.99% yes, which is a very strong yes, and you should have just closed at that. You didn't need to furthermore divide this into the no and the yes. So this is what I hope I'm able to explain the intuition behind overfitting. So let's see why it's such a big of a problem here. We have already seen why it is a big problem, but if you compare it with, say, logistic regression, if you compare decision trees with logistic regression, now we have only talked about decision trees. So if you don't understand logistic regression, you can skip this particular statement. But if you know about logistic regression, you know that sometimes you need to handcraft quadratic, cubic, and other complex features, right? Because all you have is, feature is uh, having some coefficient, right? And that's what you have, right? So if a particular output variable is impacted only if two input variables are simultaneously taking a particular value, in that case, logistic regression is not going to be able to model it very well, right? So decision tree would be able to model it very well. Decision tree does not require handcrafting quadratic, cubic, complex, and dimensional features. It handles them natively. But logistic regression would require you to handcraft those features. What that means is that it's very difficult to achieve 100% precision in training data in logistic regression. But in decision tree, it's almost always possible. And the only way it may not be possible is if you have exactly the same feature vector in two different records, one pointing to a yes, the other pointing to a no. Right? In that case, you can't split this regardless of how you split, right? So because the feature vector are exactly the same, the labels are different, and that could happen. There could be two different people who have the same age, same work experience, same everything. One of them was worthy of receiving credit and the other one wasn't, and probably that means that there was some other factor which is not expressed as a feature in our given problem, but there was some other factor that affected their credit worthiness. So barring that case, you would be able to achieve 100% precision in the decision trees. You will be able to achieve 100% precision in training data set in the decision trees, in the naive variant of decision trees. And we have already seen why 100% is bad, is actually very bad, right? So 100% precision in training data is very bad because it means you have overfitted. It means you have lost the generalization, and that's basically it, right? So it's very bad. So you have to therefore be extra cautious with decision trees. It's very hard to overfit in logistic regression because you don't have those quadratic and cubic features. But you still try to guard against overfitting in logistic regression as well by using regularization. But even if you don't do that, in general, it's hard to overfit. But in decision trees, it is, if you don't take extra precautions, you are in for a disaster. Okay. So now there are two ways we can address or we can prevent overfitting, or we can minimize rather overfitting, and one of them is pruning and the other one is random forest. I'm only going to discuss them very briefly because this one was only about decision trees, so I'm going to very quickly talk about pruning and random forest, and then we'll be done. So in pruning, we say that all nodes, we could do it in multiple ways, but one way could be that all nodes need to have at least a minimum threshold size. Any node that has less than, say, let's say that threshold is 1000. Let's say any node that has less than 1000 data points, I'm not going to consider. Okay, I'm not going to split. I'm not going to allow that node to happen. Or the other way to another way to kind of prune the tree would be the tree should not have more depth than whatever the max threshold is. So there are multiple ways. So while you still get the benefit of quadratic and cubic features that you would get in a decision tree, you're able to avoid overfitting, but there is still a trade-off. And the trade-off is, let's take this example. So let's say you had a question X, you had a distribution where you had 1,999 items, 1,999 data points. So 1000 were yeses and no's were 999. So it's almost an even split. Okay. If you ask the question X, let's say again that the question X is very awesome question and it splits evenly. It splits it very cleanly, and all the yes, all the output label yeses goes to you, go to the left child. So you would see that 1000 yeses in your output are going to the left child, and all the no's, all the output label no's are going to your right child. You know, it's just a matter of coincidence, by the way. So people shouldn't assume that the dependent variable and independent variable yeses will always coincide. This is just a matter of the particular tree that I have chosen. So all the no's have gone to the right side, okay, and there are 999 of them. Now, since I had chosen 1000 as my threshold, what would happen is it would automatically conclude that the right child is illegal, is not allowed. And since right child is not allowed, this question cannot be asked. This question has to be cancelled. And in fact, there is no other way you can split this data set in which you will have two children that are both at or above the threshold size. So ultimately what will end up happening is you'll not be able to split the parent node at all. You'll have to roll it back, kind of, you know. You can't create those left and right children. You have to cancel them. And you'll have to declare your parent node itself as the leaf node. And the parent node has very, very, very slim majority of yeses, just 50.02%. So yes wins, but very, very weakly so, which means we are going to be wrong quite often at this particular node. The problem was that you know, the right child just missed out on the threshold. The threshold was just a little above the size of this right child. I mean, ideally I should have been able to somehow ask this question without overfitting. I wanted to be able to ask this question because, you know, the right child is so close to the threshold, and this question was splitting the data in such a very clean way. But I wasn't allowed to do so because I had chosen the threshold as 1000, and therefore I ended up having a comparatively suboptimal tree, right? Because I ended up declaring my parent itself as a leaf node. So that is a trade-off that you're making with pruning. So let's look at the next option, which is random forests. So in random forests, you construct multiple, and mostly these are naive decision trees. So multiple naive decision trees. So if you construct multiple decision trees on the same data set, you'll always get the same trees because there's no element of stochasticity involved. So the way we are introducing the stochasticity is by randomly selecting some training data records and some features. So some records will get dropped and some features will also get dropped. Okay. So for each particular, so let's say if you are creating 100 trees, for each tree you will select a random set of records and random set of features, and then you'll construct the tree from there. Okay. So you may end up having a forest of 100 trees. So during the prediction, you will run the feature vectors through all the decision trees and aggregate their output. Okay, so I get an input feature vector and I run them through all the trees, and let's say 75 of those trees are saying that this person is credit worthy, and 25% of those trees are saying that this person is not credit worthy. Then I would basically say that this person is credit worthy. Right? That's just one way of doing it. In reality, you would actually add up the individual confidences of each of the decision tree, or do something of that sort. But this is just, you know, that's beside the point. The high level point is you aggregate the output from each of the decision trees. The problem with this approach, or rather the trade-off, is that because you are not constructing in any tree, none of the trees is being constructed by you looking at the full data set or looking at the full feature vector, full set of features that you have. Therefore, the nature of this problem requires more training data and more features, right? Because some of them are going to be dropped at random, right? So you will typically need more features and more training data. The other trade-off is that this is computationally more intensive because you have to evaluate each and every decision tree and aggregate the output of all the decision trees to get the final output. So therefore, there's more computation involved vis-a-vis a single decision tree. So that's the trade-off that we make with random forests. But of course, random forests do eliminate some of the, or do minimize some of the overfitting of the decision tree. Logistic regression may still work better than even random forests in the context of overfitting, but then, if your featured combinations like your quadratic and cubic features are an important constraint for you, then that might still not work out. Now, what we haven't touched here are things like how do I decide for pruning, how do I decide what my threshold size needs to be? For random forest, how do I decide how many trees to construct? These are some aspects that we need not cover here. They are, you can look up for them in the internet, or basically the technique is called validation. So through validation, you do hyperparameter tuning. These parameters are called hyperparameters, and you tune those hyperparameters during validation testing, and that's how you get the most appropriate values for your given problem statement, for your given data. So that's what this was about. This concludes this video. Hopefully this has helped you understand decision trees better. Thank you.